Namaste students. Welcome to your one-shot revision of radioactivity, one of the most frequently asked topics in your NEB board exam. In just 12 minutes, we will master the 3 types of radioactive decay, the complete derivation of the decay equation, the half-life formula, the mean life formula, radiocarbon dating, and finally, 2 solved numerical problems. We'll go through every derivation step by step. This single topic can fetch 8 to 10 marks in your physics paper, so let's get started. Hello students, let's begin our revision of radioactivity. First, what is it? Radioactivity is the spontaneous, uncontrolled emission of powerful radiation from the nuclei of heavier elements. This happens because their nuclei are unstable. Elements that show this property are called radioactive elements. Some common examples you should remember are radium, uranium, and thorium. This process is completely random and cannot be influenced by physical or chemical changes. Let's remember that key term, spontaneous emission. Now, how do we know there are different types of radiation? A classic experiment shows this. Imagine a solid block of lead with a small hole drilled into it. Inside this hole, we place a sample of a radioactive element, like radium. The lead block absorbs most radiation, allowing only a narrow beam to escape upwards. Now, we apply a strong electric field across this beam's path, with a positive plate on one side and a negative plate on the other. We observe that the beam splits into 3 parts. One part bends towards the negative plate. These are alpha rays. Another part bends sharply towards the positive plate. These are beta rays. And a third part goes straight through, completely undeflected. These are gamma rays. Let's look at the first type, alpha decay. In alpha decay, an unstable nucleus emits an alpha particle. What's an alpha particle? It's essentially a helium nucleus with 2 protons and 2 neutrons. This means the parent nucleus loses a mass of 4 units and a positive charge of 2 units. For example, radium-226 decays into radon-222 by emitting an alpha particle. See the equation here. The mass number decreases by 4 and the atomic number decreases by 2. The general form of alpha decay is a parent nucleus X with mass A and atomic number Z, decaying into a daughter nucleus Y with mass A -4 and atomic number Z -2, plus a helium nucleus. Next up is beta decay. In this process, the resulting new atom, or daughter nucleus, has the same mass number as the parent, but its atomic number is increased by 1 unit. How does this happen? Inside the nucleus, a neutron spontaneously converts into a proton and an electron. The proton stays in the nucleus, increasing the atomic number, while the electron is ejected at high speed. This ejected electron is what we call a beta particle. A classic example is carbon-14 decaying to nitrogen-14. Carbon has 6 protons, nitrogen has 7, but the mass number 14 stays the same. The general form is a parent X with mass A and atomic number Z, producing a daughter Y with the same mass A, but atomic number Z +1, plus an electron. Finally, we have gamma decay. This one is a bit different. In gamma decay, the nucleus doesn't change its identity. The new atom has the same mass number and the same atomic number as the original. So what happens? Often, after an alpha or beta decay, the daughter nucleus is left in an excited, high-energy state. To become stable, it releases this excess energy in the form of a high-energy photon, which we call a gamma ray. We represent the excited nucleus with an asterisk, like this. So, an excited nucleus X star becomes the stable nucleus X plus a gamma particle. To summarize, alpha decay changes both A and Z, beta decay changes only Z, and gamma decay changes neither A nor Z. It just releases energy. Okay students, let's quickly revise the properties of our 3 types of radiation, starting with alpha particles. Remember, an alpha particle is essentially a helium nucleus, meaning it has 2 protons and 2 neutrons. Because of this, it has a positive charge of +2e. This charge means it gets deflected in both electric and magnetic fields. Alpha particles have the lowest penetrating power. They can be stopped by a simple sheet of paper. However, they have the highest ionizing power, causing significant damage to materials they pass through. Next up are beta particles. A beta particle is a fast-moving electron that originates from the nucleus itself. They move with a very high velocity, around 10 to the power of 8 meters per second. Like alpha particles, they also affect photographic plates. An interesting property is that they can induce artificial radioactivity in certain elements. In terms of comparison, beta particles are more penetrating than alpha particles. They can pass through paper, but are stopped by a thin sheet of aluminum. Correspondingly, their ionizing power is less than that of alpha particles. Finally, we have gamma rays. These are not particles, they are high-energy electromagnetic waves, or photons. Since they have no charge and no mass, they are not deflected by electric or magnetic fields. Gamma rays travel at the speed of light. They have some unique effects, like producing fluorescence on certain materials and generating heat on surfaces they strike. Most importantly, they have the most penetrating power, requiring thick lead or concrete to stop them, but they have the least ionizing power of the three. Now, let's state the fundamental laws of radioactive disintegration. There are 3 key points. First, radioactivity is a random and spontaneous process. It cannot be influenced by external factors like temperature, pressure, or electric fields. Second, during disintegration, an unstable atom emits either an alpha particle or a beta particle, often followed by a gamma ray. The third and most crucial law for our derivation is that the rate of disintegration at any instant is directly proportional to the number of atoms present at that instant. This next part is a very common exam question, the derivation of the decay equation. We start from the third law. The rate of disintegration, dN by dt, is proportional to the number of atoms, n. To make it an equation, we write dN by dt equals negative lambda n. Here, lambda is the decay constant, and the negative sign shows that the number of atoms decreases as time increases. Now, we separate the variables. We get dN by n equals negative lambda dt. The next step is to integrate both sides. Integrating gives us the natural log of n equals negative lambda t plus c, where c is the integration constant. To find c, we apply the initial condition. At time t equals 0, the number of atoms is the initial number, which we call n naught. Substituting this, we find that c equals the natural log of n naught. Now, put this value of c back into our equation. We get natural log of n minus natural log of n naught equals negative lambda t. Using log rules, this simplifies to the natural log of n by n naught equals negative lambda t. For the final step, we take the exponential of both sides. This gives us the famous radioactive decay equation, n equals n naught times e to the power negative lambda t. This shows that the number of undecayed atoms decreases exponentially with time, as shown in this graph. So, what exactly is this decay constant, lambda? We can define it in 2 ways. First, from our starting equation, we can rearrange it to see that lambda equals the rate of disintegration, negative dN by dt, divided by the number of atoms, n. So, it is the ratio of disintegrations per second to the number of atoms present. The second definition comes from our final decay equation. What happens when time t equals 1 by lambda? If we substitute this in, we find n equals n naught times e to the power of negative 1. This means n equals n naught divided by e, which is about 36.8% of the original number of atoms. So, lambda can also be defined as the reciprocal of the time during which the number of atoms in a sample falls to about 37% of its initial value. Fundamentally, lambda represents the probability of decay of a single nucleus per unit time. Hello students. Let's begin with half-life, a key concept. Half-life is the time required for half of a radioactive substance to disintegrate. We denote it T1/2. For the derivation, we start with the decay equation, n equals n naught e to the power negative lambda t. Now, by definition, at time t equals T1/2, the remaining number of atoms, n, is n naught by 2. Substituting this, we get n naught by 2 equals n naught times e to the power negative lambda t 1/2. We can cancel n naught from both sides, leaving 1/2 equals e to the power negative lambda t 1/2. Taking the natural log on both sides gives natural log of 1/2 equals negative lambda t 1/2. Since natural log of 1/2 is negative natural log of 2, which is negative 0. 1693, our equation becomes 0. 1693 equals lambda times t 1/2. Therefore, the half-life t 1/2 is 0. 1693 divided by lambda. This clearly shows that half-life is inversely proportional to the decay constant. Next, let's discuss mean life, also called average life. It's defined as the ratio of the sum of the lifetimes of all the individual atoms to the total number of atoms present initially. We denote it by t-mean. While the full derivation involves integration, the result is very simple. The mean life, t-mean, is simply equal to 1 divided by lambda. So, the mean life is just the reciprocal of the decay constant. We can also relate it to half-life. Since t 1/2 is 0. 1693 by lambda, we can write t-mean equals t 1/2 divided by 0. 1693. This evaluates to t-mean equals 1.43 times t 1/2. So, the mean life is always longer than the half-life. A fascinating application of radioactivity is radiocarbon dating. This is a process used to determine the age of ancient geological and archaeological objects like fossils and artifacts. It works because cosmic rays create neutrons that interact with atmospheric nitrogen-14. When nitrogen-14 absorbs a neutron, it forms carbon-14 and a proton. This carbon-14 is radioactive, with a very long half-life of 500 years. Living organisms absorb this C14, but stop when they die. By measuring the remaining C14, we can find the age using the formula t equals 1 by lambda times the natural log of n naught by n. Or more practically, t equals t 1/2 divided by 0. 1693 times the natural log of a naught by a, where a is the current activity. Time for a numerical. A substance has a half-life of 5 years. How long until 75% of it decays? First, let's list our given values. t 1/2 equals 5 years. Now, if 75% has decayed, this means only 25% remains. So, the number of remaining atoms, n, equals 25% of n naught, or n equals n naught by 4. Let's use the formula, n equals n naught times 1/2 to the power t by t 1/2. Substituting our values, we get n naught by 4 equals n naught times 1/2 to the power t by 5. Canceling n naught gives us 1/4 equals 1/2 to the power t by 5. Since 1/4 is the same as 1/2 squared, we can write 1/2 squared equals 1/2 to the power t by 5. By comparing the powers, we get 2 equals t by 5. Therefore, t equals 10 years. Our final answer is that it takes 10 years for 75% to decay. Let's do one more, this time on carbon dating. The question states, the activity of a fossil is found to be 1/4 of the activity of a living specimen. If the half-life of carbon-14 is 500 years, find the age of the fossil. Let's write down the given information. The current activity, A, is a naught by 4. The half-life, t 1/2, is 500 years. We use the same formula as before, but for activity, A equals a naught times 1/2 to the power t by t 1/2. Substituting the values, a naught by 4 equals a naught times 1/2 to the power t by 500. Again, we can write 1/4 as 1/2 squared. So, 1/2 squared equals 1/2 to the power t by 500. Comparing the exponents, we find that t by 500 equals 2, therefore, t equals 11 years. So, the age of the fossil is 11 years. Finally, let's quickly cover some other uses of radioactivity. In medicine, radiophosphorus is used for treating skin diseases and leukemia. Radioiodine is used to check the condition of the thyroid gland. In agriculture, gamma rays are used to preserve food for longer periods by killing microorganisms. Radiation can also cause mutations in plants to develop new, improved varieties. In industry, nuclear radiation is used in the production and modification of plastics and other materials. While useful, radiation also poses serious health hazards. Strong alpha-ray exposure can cause lung cancer. Exposure to fast and slow neutrons can cause blindness. Neutrons, protons, and alpha particles can damage red blood cells. Strong proton and neutron exposure is also known to damage reproductive organs. Because of these dangers, strict safety measures are essential. Workers often wear lead aprons, radioisotopes are handled by remote control, and any nuclear explosions are carried out far from public areas to minimize risk. All right, that's a wrap. Just remember these key formulas: the decay equation N equals N naught e to the power negative lambda t, half-life T1 half equals 0, 1683 divided by lambda, and mean life T mean equals 1 divided by lambda. If this video helped, hit subscribe and like. Drop a comment on which chapter you want next. Coming up next is the Modern Physics one-shot for your NEB board exam. Stay tuned.